Welcome to a short discussion about statistics that we'll be using in the labs. The idea of statistics are to interpret data and to establish uncertainty. Most of the material we'll be talking about here is in Chapter 2 of the book, Measuring the User Experience by Tom Tallis and Bill Albert. We use statistics because eyeballing the data can be misleading, and we require objective proof when we want to say that something is larger than something else. So statistics provide us with a consistent method for establishing proof, and when they're combined with a good experimental design, they help overcome our natural biases and assumptions. The main idea is that we have causes and effects, and we want to use independent and dependent variables in an experiment to see which causes and effects are actually happening. So independent variables are things you manipulate or control for, and dependent variables are the things that you measure. And we'll give you an example. So we start off in an experiment and we change the independent variable, we observe the effect on the dependent variable, we use statistical analysis to see if there's a significant effect on the independent variable on the dependent variable, and then we interpret the results, usually with some kinds of charts or diagrams. So in Lab 1, you're going to be doing a mental rotation experiment, and here the independent variable is going to be the amount of rotation between two images that the person has to compare. The dependent variable is then the time taken for the person to decide whether or not the two images are identical. So there are two identical images, but one of them has been rotated compared to the other. The statistical analysis will then be to look at whether more rotation of the image in the stimulus leads to longer decision time in the response. And if we find that, then the interpretation is that because there's more rotation in the stimulus leading to longer decision time, this suggests that people are using mental imagery to rotate the images in their heads. And this is a classical experiment which really got people to believe that people can do mental imagery because they have this kind of rotation process. So what we need to know for the labs is, first of all, being able to report descriptive statistics, such as the mean and the median and the standard deviation, being able to report confidence intervals and using them to construct error bars, and this will allow us to see how uncertain we are about where the true value of the mean is if we're reporting, say, a bar chart with the mean. And we'll also carry out simple statistical tests to compare means and analyze relationships between variables. And finally, and very important, in your reports, you'll be doing visual presentations of the data as scattergrams, bar charts, or line charts. So the mean and median should be familiar. The mean is what most people think of as the average, and it's the sum of all values divided by the count of those values. The median is the middle number in a series, so when you have the median, half the values are going to be below it, and half the values will be above it. You can use Excel very easily to calculate the mean. It's just the average function, and similarly, the median can be calculated in Excel as the median function. The variance tells you how spread out the data are, and the more variance you have, the more variation you can expect to find in data points. So just by chance, when you compare two sets of numbers, even if there's no real difference between them, because of variation, you may see some differences in the sample means. So the formula for calculating the variance as explained in words on this slide. There are also formulas that are available and very easily on the internet or in textbooks. And the thing to note is there's also a thing called the standard deviation, which is simply the square root of the variance. And both the square root of the variance, standard deviation, and the variance itself can be calculated very easily using Excel. So next idea is a confidence interval, and this is the idea that when you have a sample mean, it's going to be a noisy estimate of the true mean or the population mean. So if I try to find the average height of males in Toronto, for instance, I might take 10 people at random and measure the sample. But if they happen to be a basketball team, I might get a much higher number than should be the case for the population. So the confidence interval is a way of saying this is how certain we are that the sample mean is close to the population mean. And the confidence interval is actually the region that we expect the true mean or the population mean to be in, given the variation in the data. So a confidence level of 95% means that we're 95% sure that the true mean is in the range, the confidence interval that we've defined. On the flip side, if we're 95% sure, then we're 5% unsure. So now there's a 5% chance that the true mean could actually be outside. Why do we choose 5%? Well, the idea is that 1 in 20 is a pretty good cutoff for surprise. So most of the time we're going to be right if we assume that the true mean is actually inside the 95% confidence interval. Occasionally, however, we're going to be wrong, but it's a trade-off, right? Because if we try and make the confidence interval too big, it's going to be very wide, and it will be less informative. So the confidence interval is calculated by the formula shown below. This 1.96 number that you multiply the rest of the equation by is actually derived for normal distributions, and only applies for normal distributions. So this is, if you like, a way of calculating fairly thin confidence intervals, and for most other data where you don't have a normal distribution, the multiplier will probably be a little bit over 2 to about 2.5. And here you would use a t-statistic, but we'll talk about t-tests in just a minute, but it's good enough for this class if we use the 1.96 multiplier. You can calculate a confidence interval in Excel by using the formula shown at the bottom of the slide, and here you'll be able to specify the alpha value. That's the kind of 0.05 or something like that, which says your what's outside the confidence interval, the chance of being the true mean being outside the confidence interval. You'll also put in the standard deviation and the sample size to make the calculation. Here we see an Excel spreadsheet screen, and you'll see at top in the ellipse the statement for the confidence interval function, and it has 3 arguments or parameters. You have the 0.05 showing that this is a 95% confidence interval because you're only 5% uncertain about the true mean not being inside the interval. Then the second argument is going to be the range of numbers that are being used and where you calculate the standard deviation. And the final parameter is going to estimate the count from the same column of numbers. In this case, it's column B, and we're looking at the confidence interval associated with the task time. So the answer in this case is that confidence interval is 6.4. This means that the range of the interval is plus or minus 6.4 around the sample mean. So you can, I strongly suggest that you practice and make sure you can do this before the lab so that you're more efficient when you're doing all these manipulations inside the lab. So in this sample data, we have 2 designs, A and B, and we're going to calculate the 90% confidence interval for these 2 items using the method described in the previous slide. You can then construct a bar chart and put error bars on each bar in the chart, and the error bars will represent the 95, or in this case the 90% confidence interval around the mean, where the mean is the top of the bar. Let's move on now to t-tests, and they're a very important statistical test that looks at 2 samples of data and decides whether or not the means of those samples come from the same distribution. In other words, the question is, are these two samples driven by the same process, or are they different? So if we were measuring the height of females in Canada and the height of females in the United States, and we took a sample of 100 people from each country, then we might use a t-test to decide whether there's a true difference in height or not. So the idea of a t-test is you divide the difference in means by a measure of variability, and then you check against a statistical table of t-values, and then based on the number of observations you're using, you come up with a probability that there is in fact a significant difference, and this probability is called a p-value. The other thing to note is that there's different formulas depending on whether it's a paired test or an independent test. So an example of a paired test would be if we're looking at shoe wear, and we have shoes on the left and the right foot, and each person's wearing a slightly different model of shoe, and we want to see if the two models of shoes wear out differently, and we're measuring, say, the amount of wear on the sole as the dependent measure. That would be an example of a paired test because every observation can be compared between the left and the right foot. An independent sample would be if we had each person wearing a pair of shoes and there's only one model of shoe on each person. So in this case, different people are wearing the two models of shoes, and it becomes an independent samples test. So here's an equation. We're not going to refer to it in the class. I just want to show you that the equation exists. And this is for a paired t-test. And you see here that there is the mean of the differences at the top. Mu0 is just in the case that you're expecting a particular difference. Normally we expect a difference of 0, so that term will drop out. But occasionally you want to, based on previous research, look for a difference of a certain size, and then the t-test assesses whether or not you're getting a difference of that size or not. On the bottom of the equation, we have the standard deviation of the differences, and it's divided by the square root of n. And there's a whole lot of statistical theory behind this that you don't need to know. All we care about in this class is being able to apply the methods. And here again, we have the independent t-test. It's a bit more complicated, but you see at the top we have a difference in the sample means, and it's being divided by a measure of variation. Don't worry about these equations. We're not going to test for them, but I just wanted you to know that these things exist. So here we see the t-test being carried out in Excel, and you'll notice here that there are 4 arguments to the term or the function. We first of all have the B2 to B9 telling us which data we're sweeping out in the spreadsheet, and in this case we're looking at design 1 because we're in column B. And then the second argument shows that we're also looking at design 2 in column C, and it sweeps that out. The third parameter tells us how many tails we're looking at. So the idea here is that we could be looking for simply a difference between design 1 and design 2, and that means it doesn't matter if design 1 is bigger or design 2 is bigger. That's called a two-tailed comparison. On the other hand, we could have a hypothesis that says that design 2 is bigger or has a higher score than design 1. So in this case, that would be a one-tailed test. So if we look at the t-test function at the top in the ellipse, we'll see that the parameter is 2, telling us that it's a two-tailed test, so we don't care which one is bigger, we're just looking for a difference. And finally, the type of test in the fourth parameter is also a 2, and this says that it tells Excel that this is an independent samples test. So it will use the second equation you just saw. Okay, so you can see how to do a t-test in Excel, and it's a very straightforward calculation. Doesn't require you to understand the equation necessarily. And you'll see here in this t-test, we've also, as well as getting the, we get a value of 0.047. So what does that mean? That's called a p-value, and it tells us the likelihood that these two designs are really the same thing or having the same effect. And so it's under It's under 0.05, meaning it's less than 5%. So normally in statistical analysis, we would decide that that is statistically significant. Now these days, people are getting away from p-values and find them not very useful, and so they're often just looking at the error bars and the confidence intervals and deciding how strong the effect is, rather than is it significant or not. But in this class, it's okay to talk about significance p less than 0.05. Okay, so t-test is significant, and it looks like there probably is a real difference in design 1 and design 2. On the right, you'll see we have the bar chart to show this difference, and you'll see that again we have the error bars as 95% confidence intervals, and because the means of, say, if you look at design 2 mean, you'll see it's outside above the top of the error bar for design 1. So this is a pretty good visual representation of the difference, and suggests that there likely is a difference between these two designs. Here we see another example, and this is a paired t-test. So each person gives an initial rating and then a final rating. So here we've got a very different result. If you look at the p-value, which is highlighted, what you see is that it's like 0.0002. In other words, there's very little chance that these initial and final ratings are the same. It seems that the person's ratings increased for whatever reason from the initial to the final. It could be because they received more information, or because they got more experience, but the numbers are showing an increase. And again, if you look at these ease of use ratings on the right in the bar chart, you'll see that the confidence intervals, or the error bars, are not overlapping with the other means. So what if you want to know about the relationships between variables? So an example would be height and weight. As height increases, weight tends to increase, and that's a positive relationship. So we can visualize relationships in Excel using a scatter plot, which will be shown in the next slide. And then the line that runs through the data is called a trend line in the scatter plot, and it can be added to the chart in Excel by right-clicking on any of one of the data points and selecting Add Trend Line. So here's a scatter plot with a trend line, and there's a value here which says R squared equals 0.26, and this indicates the strength of the relationship. Notice the lines going from the top left to the lower right. What do you think that means? Well, it means that as the task rating goes up, the mean task time is going down. This is called a negative relationship. If we wanted to have a positive relationship, we would be expecting the task time to go up as the mean task rating goes up. But in this case, it's good if you take less time to do the task, so it's natural for people to feel more comfortable about the task and giving a higher rating when they take less time. And the correlation can be done in Excel using the correl function, and in this case there are two arrays as arguments, and these represent the two sets of numbers to be correlated. The result will then be a correlation coefficient commonly referred to as R, and the closer R is, R can vary between -1 and +1, and the closer it is to -1 or +1, the stronger the relationship, and if it's 0, there's no relationship. Notice that there's nothing wrong with -1. We can simply redefine a variable, and the correlation can change from -1 to +1. So if, for instance, for mean task time, if we defined it as speed or quickness, then the correlation would become positive. Here's an example of a bar chart with error bars, and this is a nice way to present data, and you can also visually compare across and see fairly easily which differences are likely to be significant. So in this case, the add to cart bar is higher than any of the other bars, and the top of that bar is above the error bars for all the other activities or components. So clearly there's a significant difference between add to cart and all the other functions. On the other hand, if we look at the right, we see that check status and post review have some overlap. So there's no significant difference there. And the same is true for login and search on the left. So a bar chart with error bars is a great way of visualizing whether differences are significant or not. Another way of doing it is a line chart. And a line chart is interesting because it allows you to plot different factors. So in this case, we have 4 trials going along the x-axis, and we have 3 designs represented by 3 different colored lines. And what we see here is that design 2 and design 3, the green and the red lines, start off different on trial 1 but converge by trial 4, whereas design 1 in the blue line has a shorter time regardless of trial. So the relationship between the blue line and the other lines is roughly parallel, whereas the relationship between the red line and the green line is one where they start off different and then merge together. We can also use the error bars to look for significant differences, and we can see very clearly that the blue line or design 1 is better in terms of time, taking shorter time all through the 4 trials. So that's a brief introduction to stats, and it should be enough to be able to successfully carry out the labs, the 4 labs that you'll be using in this class. The statistics and charts that we presented here are important because they're going to be used in the experiments that you'll be running, and they're also things that everybody should know, and they allow you to interpret scientific data and read scientific publications. Good luck with the labs.